Okay, here we go. The last one of these on the list. And I'm going to scroll up. And now we'll go over it in detail. And so we have a spring being compressed with a force probe. And the force is a function of how much we compressed it, is shown in the table. And we want to make a graph. And so we take our points in centimeters, so it's centimeters here, but watch that for later. And then force in newtons here, and we plot our points, and we draw a best fit line. And so it should go right through the middle of those points, some above, some below, should come real close to going through 0, 0. And then we're asked to use our graph to determine the spring constant. And so this data doesn't exist anymore. Once I've graphed it, now it's this line. Don't use your data from then on unless they ask you to do another graph. And so we want to determine the spring constant, and so that's the slope. Also says show your work and record your answer on the graph. Plenty of room. And so I picked 2 points. I picked this one because the line crosses really easy to read point. And then I did pick 0, 0, but notice I'm showing I used 0, 0. I did not pick 1 point and get the ratio of y to x. That is not a slope, never has been, never will be. And so 8 minus 0 is a change in y. I converted centimeters, 40 centimeters is 0.4 meters. And then I get 20 newtons per meter, and then I record the answer below as instructed. And if you're anywhere between 18 and 22 and showed your work on the graph, should have got all those points. Then we put the spring on a horizontal frictionless table fixed to a wall, and we compress it 40 centimeters from its uncompressed length. Calculate the work done by the spring. And so we're compressing the spring this way. The force from the spring is in this direction, so that's going to be negative work by the spring. And the equation 1/2 kx squared for a linear spring, and I put in 1/2, I put in whatever my k is, and 0.4, so any k should have got you the points, even if you were off. And said include the units though, and so you had to have joules here to get both points. And now we're going to let go of the spring after we've placed a 0.6 kilogram block in front of it and things are frictionless. And so how fast will it be going when the spring is still compressed 25 centimeters? So we pushed it in 40 centimeters and it's still compressed 25. And so this would be x initial, and this would be x final after you convert to meters. And so the initial energy is all elastic, the final energy is elastic and kinetic, and so 1/2 kx squared equals 1/2 kx final squared plus 1/2 mv squared. The 1/2s go, put in whatever your value is for k, times 0.4 squared, so that's x initial, 0.4, and then times x final, 0.25, 0.6 v squared. Solve for v, you get 1.8 meters per second. And so the block gets launched and it's cruising along the frictionless table, and I want to know if it landed 1.8 meters from the edge of the table, how high was the table? And so first you have to figure out how fast it's going, and so that would mean all of the energy goes into kinetic, and so all 1.6 joules from up here goes to kinetic, so it's going 2.31. If you use your answer from D, you're not going to get full credit. Don't feel bad. When I worked out the key, I think that's what I did first time through. And so no, it's going a little faster, right? The spring is finished pushing on it. And so I look at the x motion and the y motion separately. If you look at the y motion first, you'll see you have 2 unknowns, the height of the table and the time. So then if you look at the x motion, I know the final x started at 0, I know the x velocity is all, this is all in the x when it goes off. It's all for the time. Now I can put that time into the y motion equation and solve for how far it went. Or how far it fell, 2.98 meters. That's how far anything falls in 0.78 seconds. The 2.31 does not affect the y motion at all. It just helps us figure out the time in the